Hello, my name is Srikantan Sankaran. I'm an architect in the Microsoft Technology Center in Bangalore. I've worked in Microsoft for close to 16 years now. I started off as a consultant and then an architect in the consulting services division. I worked as a technology evangelist in the developer experience team. I was a cloud solution architect, and then I worked as a principal engineer in the commercial software engineering organization before joining MTC. I'm here to talk to you about this scenario related to bulk data ingestion. So this was one of the customer projects that we worked upon, which involved ingestion of large amounts of data from a data lake into different database technologies. And then we had to benchmark and sort of arrive at the most optimal and performant way to achieve that. So let me delve into the details. The use case related to this involves users uploading a lot of information. These are actually called business entities or objects. And these had a notion of a parent and child entities. A single entity could have up to about 60 million records as well. And all of these are actually processed together. There are a lot of business rules and then validation rules applied on top of that. And the entities undergo a change in the life cycle status as well. But not all these steps happen in quick succession. It could so happen that once they reach a particular stage, they may have to remain in that state for a couple of weeks or even months at a time before they are actually taken up for subsequent processing. All along, the business problem was that for this particular duration where the data just sort of sits there and nothing's done on it, it ends up taking expensive storage as well as the compute that the database has to offer, which would have been better utilized to process the new entities that need to be uploaded into the application. So which is when we added up an option where we said, let's sort of hydrate or sort of export this information into a data lake store where the storage is extremely cheap. And then whenever required, this data could be quickly resurfaced back into Azure, into the database where it could be taken up for further lifecycle processing. The first part of the process where the data needs to be pushed from the database into data lake store, it's easily achieved because it's just a question of running a Spark job, which is going to run a query on the database, extract the information, and quickly write them to the Parquet data store. But what was of concern to the customer is how optimally and how quickly could we bring the data back into the database from data lake store. Obviously, it's not going to be that easy. We have things like the database indexes to contend with. So obviously, it's going to be slower than the data export process itself. So for this, we had three different approaches that we benchmarked on. One was using the option of an OLTP database. So we used Azure SQL Hyperscale for this. We know that it supports a row store index. So an OLTP database is highly tuned for high volume, high concurrency transactions on a subset of data. That's what it's actually geared to meet. We then also explored an option with an OLAP database like Synapse Data Warehouse. Synapse has a notion of a clustered column store index where it stores the data in a columnar format. Data is highly compressed and it lends itself for very performant analytical queries on top of huge volumes of data. The third option, which is called the HStack, which indicates hybrid transaction and analytical processing, is a combination of both OLTP as well as OLAP capabilities in the same database. Azure SQL Hyperscale has this notion of the NCCI or the non-clustered column store index, which together with the row store index that it supports, gives us a combination of both these capabilities on a single technology. So we also wanted to see how this particular option sort of performed in the benchmarking exercise. This is as far as the database technologies go. We also had evaluated multiple options for the compute. One was using Azure Databricks, which, as we all know, is a managed Spark offering on Azure for connecting the data store, the data lake store, and then bulk inserting them into the database. The other option that we looked at was Azure Data Factory, which is a managed service in Azure, where using a user interface, one could compose an ELT or ETL pipeline to move and transform data along the way. The focus of this particular talk is restricted to the part where we work on the Azure Databricks alone. The diagram here depicts what I just covered. The fact that we use the Databricks Azure Databricks part to pull data from ADLS and benchmark the insertion into each of the Azure SQL Hyperscale OLTP, Azure Synapse Data Warehouse, and then the XTAB with SQL Hyperscale. Let me talk a bit about the database options and the indexing different strategies considered. With the OLTP database, we'll be using the row store index, which is the conventional way to store relational data in a table with rows and columns. And these are physically stored in a row-wise format. The table would typically comprise of a cluster index, which is the primary key, and then it could contain one or more non-clustered indexes as well. For the sake of publishing this benchmark to the wider audience, obviously we have not used the customer data sets and the schema there. So instead, we have recreated the benchmark exercise using a sample data that is published by the TPC DS benchmark. So in fact, we have used this particular data set, and it has about 1 TB worth of data. And it comes with a toolkit which can be downloaded, which helps to deploy all the necessary the data sets and then the T-SQL scripts with which we create those databases. It provides sort of help with all of that. So while I'm on this page, I just want to tell you that this is actually a blog article that we wrote about 2 years back when we after we completed the customer engagement. And this comes in actually a 3-part series, okay, and it's quite elaborate, and then it delves into a lot of details, of which I'm going to talk of learnings and summary information, which is meant for this audience. So I would strongly recommend that people could refer to these blog articles to go into more detail on specific aspects that interest or suits them. This dataset has numerous data sources, but for us, for the benchmarking exercise, we have taken 3 tables alone. One is the a store table, which contains a list of store IDs, and then there is a store returns and a store sales table, which contains transaction information, and one of the columns in those tables refers to the store ID that is existing in this particular table. So the store returns and the store sales tables have a surrogate key, which means they have a secondary key, which is the store ID itself. And actually, when I go through each of those runs for the benchmark, I'll walk you through the schema of these tables. But at this time, I just want to convey that we will be using these 3 tables for the exercise. For the clustered column store index option, so we'll be using Azure SQL Synapse Data Warehouse. With the clustered column store index, the data is stored in a columnar format. It is used in data warehousing scenarios to execute analytical queries because it actually provides a high level of compression, which means it's going to leave a relatively less amount of footprint on the storage layer. And then it provides magnitude, several magnitude more times of query performance as well for analytical workloads. For the NCCI index on the HTAB database, we'll be using Azure SQL Hyperscale database. This is a variant of CCI. It's called the non-clustered column store index. While this is a columnar index, it actually works on the row store table as well. So, which is why it's able to give the capability of being able to run analytical queries effectively on top of data in the row store data as well. So while I speak of NCC as one of the options with which HTAB capabilities come to the fore, Azure SQL Database also has this notion of an in-memory capability, which means that the data is cached in the database. So which means read queries can actually be much quicker because they talk to the in-memory cache as well. So this also is in a way of providing you both a strong capability to run analytical queries while at the same time being able to cater to transactional workflows as well. Let's discuss the outcomes from the benchmarking run on the row store index. But before that, I just want to also mention the fact that for the row store index, the bulk ingestion was done in two methods. The first method was where we performed a sequential data entry into every table. For example, we have three tables here, and then we would actually insert table one after the other. And then we also captured the benchmarks when the operations were done concurrently. So let me talk a bit about the environment itself. So we had a Databricks cluster. It was actually standard SKU cluster running the Databricks runtime version 6.6. It had two workers in it. It was actually the standard DS3V2 SKU that we use, which comes with 14 GB and memory and then 4 cores. We use the Microsoft Spark connector. I want to convey here that the Spark connector comes in two forms. One is the recent, which is the Microsoft SQL Spark connector mentioned here. And then previous to this, we had the Azure Spark connector as well, which is actually now deprecated. During the benchmark, we used both these connectors and then we have published those results. But for the sake of this session, I'm going to sort of restrict myself to the Microsoft SQL Spark connector. So this jar file was deployed and then it was used in the Databricks notebooks. For the capture of metrics itself, we used the tool called code timing, and then we used Alt-Type for all the charts that were displayed in it. As far as the database goes, so we used Azure SQL Hyperscale, and then we started off with a 2-version code. Because we're going to perform stuff sequentially, we thought this was a good to start with, and then this is what we used, and it had 0 replicas. For the source data itself, we used Parquet files, and I'll talk to briefly about how that data itself was stored on that ADLS Gen 2 location. I already mentioned that there are 3 tables here. One is the store returns, and the store sales table. And the only the returns and the sales table had a surrogate key, which was actually store ID pointing to the store table itself. The data from these 3 tables were exported to ADLS Gen 2 as Parquet files, and then they are partitioned based on the store IDs. To explain more about what I'm seeing here, so let me take you to the blog post here. And as you see here, so this is how we sort of partitioned the data and before we wrote the ADLS Gen 2 location. You see that there is one partition for the store ID itself. The reason behind choosing this particular column to partition norm is that once this data is pulled back into the database, all the typical the lifecycle steps that happen downstream at that particular stage involve filtering and querying on these tables based on the store ID itself. So it made sense for us to partition the data, the source data itself based on the store ID, and then subsequently all the indexes in the tables that we'll create will also, the surrogate index that I just spoke of, will also use the store ID for these reasons. We then ran the Databricks notebook and then sequentially uploaded and ingested all the data into the 3 tables. In all, we could upload 55 million records in about 35 minutes or so. This particular table here gives you a breakup of the outcomes from that run that we captured in the notebook. So there are 5 different unique store ID values for which we ran the notebooks. So the columns here indicate the time it took to insert records into these tables for each of the store IDs. So in all, for the store ID 529, it took an addition of all these three, which is about 311 seconds. So in all, it comes to about 30 minutes or so across all those tables. So while the entire ingestion process was successful, we had a look at the Spark logs themselves, and then you were surprised to see that there are a couple of entries indicating failure. So there were some deadlock errors from SQL Server that are thrown along the way. But because of the goodness of Spark, which inherently tries to retry So eventually all the ingestion operations succeeded. But it was good to note that we had these errors, and then going forward, we'll see how to tackle this and make sure that we optimize the input process in such a way that we're able to avoid this and then make it extremely performant. So at this time, I just want to take you through the walk you through certain steps in the data that were actually implemented in the database notebook. Um, So like I told you, from the database notebook, we'll actually query the Parquet files and then passing the store ID value as a parameter and get the data for that particular store ID alone into the data frame. And then this would be then pushed to the Azure SQL database into that particular table. So that is sort of explained in this particular step, where we read the Parquet file from the root path, store the table name, and within that we actually further filter that on based on the store ID that we're interested in. The rest of the parameters are not so significant at this point in time, so I'll let me just gloss over them. And probably let me come back to the presentation here to I just want to think if there's anything that I need to convey at this point, but I think I have conveyed all the key aspects of this particular run. So a sequential table insert was for 55 million records was completed in about 30 minutes of time. And there are some errors which actually were covered up because Spark retried those operations and eventually we were able to successfully upload all that information. So the next step we did was to perform the same step using a concurrent table insert. So obviously this needs more compute power. So which is why before we ran this, we increased the capacity of the Databricks to hold 8 workers. And then we also sort of scaled up the SQL Hyperscale database from 2 vCores to 8 vCores. We made some changes to the Databricks notebook themselves to take care of certain additional aspects because we wanted to run these inserts in parallel. So we use the Python's multi-threading library to submit multiple jobs concurrently. And then we also took care to coalesce all the data partitions for a particular store ID in Spark data frame because we didn't want to land up in the same situation as in the previous case where we bulk insert two volumes of data into a single table and then we have the content with the deadlock and all those issues. While Spark would retry and complete those successfully, but still we wanted to see if we could avoid them by coalescing all the partitions for a single store ID. So let me explain what I'm talking about here. So if I go to this particular, the second post in the blog, which covers this particular run of the Databricks job, you notice that this is how we can either switch on or switch off the coalescing of those partitions. So we have captured the outcomes from this particular run in this table. You would notice that, and we also have actually embedded this particular chart, which gives a comparison of how the sequential run sort of compared against the concurrent run for each of these two varieties in question. So very evidently, you can see that the concurrent runs took much less time, comparatively less time with the sequential run. But what is important here is that for the concurrent runs, we should be adding the individual times it took for each of those store IDs because we should be taking the max of what it took for them because the runs were all happening in parallel. So learning from this particular exercise was that when we actually implement partitions in the when there are partitions in the data frame, the SQL Spark connector will initiate bulk import for each of these partitions concurrently. This will result in multiple inserts happening on the same table, which causes race conditions with page locks and all of that. So that's learning that we derived from this particular exercise. I just realized that I missed sharing the walking you through the T-SQL scripts with which we created the tables and created the index. So let me quickly step into the blog article and please Pradeep, it have repo for that. So if you navigate to the SQL folder, you see that here are where all the SQL scripts are located. So let me open this particular script, which is about creating the tables, the three tables that we discussed here. The first is the stores table, which contains these attributes, and it has a primary key, which is cluster. It's a combination of the item code as well as the ticket number. Then we also have a store returns table, which also has the same set of keys as the primary keys. And then we have the stores table, the master table, which contains the list of all these store IDs. And this is clustered on, has a clustered index on the store ID as well. And each of these tables have a particular column which has the store ID in them. Sorry, this is this particular column. And so does the sales returns, the store sales as well. And then you have one more SQL script file which contains how the secondary indexes were created for the store table itself. You see that it has one particular index on the store ID as the secondary index. And the store's sales table also has the secondary index on the store ID as well. And ditto with the case of the store returns table as well. So with that, let me go back to the presentation. So at this point, we have covered the benchmark results for bulk insertion of data into the row store index, both performing an insert sequentially across those tables, and the next stage of that operation, we also perform the concurrent table insert. And then the inferences we had so far, where with the concurrent table operation, obviously it was much faster, and then and the deadlocks still surface themselves, and then do Spark read side and sort of eventually succeeded to put through all those records as well. So we'll deal with these deadlocks in the ensuing slide. So for now, I want to move on to the next stage of the ingestion process and the next scenario, which involves the use of Azure SQL data warehouse. Like in the previous case, we did not change the compute because we wanted to compare the results for equivalent capacities on the Databricks notebooks and then Azure SQL Synapse data warehouse as well. There were some changes that we performed to the Databricks notebook, the Python code in the notebook. Some of the important changes that we made were actually the one that you see here. So when you connect to the SQL database, so there's certain options that can be specified. Apart from the usual connection string and the associated parameters, we can also specify something called a batch size. So this particular number here indicates it indicates a number of rows. I mean, any number of rows below this particular number, it means that Synapse data warehouse is first going to ingest the data into a delta store, and then the next stage of the input process is going to dump them into the row group inside the table. So in case we want to skip this two-step process, we can specify a value which is more than this number that is specified here, by virtue of which the database engine knows, and then it directly pumps the data into the table row group itself. So that's one important change that we found in the code. And apart from that, a few other changes that we did was, because at this time we know that the clustered column store index, we didn't anticipate getting the same kind of the deadlock issues and all of that. So we removed the flag with which we were actually coalescing all the data frames for a single for multiple partitions. We actually let the number of partitions be as they are without coalescing them. And then when we actually went through the database, the Databricks notebook run, we found that there wasn't a single error in the process, and the entire set of 55 million records were inserted in just under 4 minutes. So you can say that this is order of magnitude times faster than it was with the row store indexes as well. So let me walk you through the SQL scripts that were used to create the clustered column store index. So when you look at this particular folder, you see the cci.sql. I'm opening that file now. So this is the script which the table itself was created, and then here is where you actually create the clustered column store index on the entire table. This is all that needs to be done. Okay, so let me also walk you through the code where we actually made this run. Okay, so this section of the blog post gets into much more detail. So we are stating here that we do not have to coalesce the partitions because the CCA index was with the CCA index, it was possible to insert parallelly into the same table without landing into those issues that we faced earlier. And the significance of the batch size also what is described here. I think these are some important things to keep in mind when we go through this. So when you look at the database resource consumption itself, you see that it was extremely efficient. The CPU really spiked during the 4-minute duration for which the database run happened, and then after that it was actually came back to normal. So a key conclusion that we sort of arrived at from this is that CCA are meant for large-scale ingestion scenarios and works great with bulk inserts and reads. Next, we move on to the third scenario in the bulk ingestion scenario, which uses the non-clustered column store index. We'll be implementing this using Azure Hyperscale database, and then we'll create an SCCI index on top of it. So here we go. So we want to look at where the script file is to create the non-clustered index. So this is the file that we need to look at. You'll notice that so this is how you create a non-clustered column store index on this particular on the sales table. While we could have chosen only specific columns that would be required as a part of the index, but here we just chosen the worst case scenario, and then we thought we'll measure how the performance how it performs, which is why we added all the columns into this. Yeah, one thing to note here is that the NCCI is going to take much more space than just the row store index because it needs to store the data from the column index as well. But the data is highly compressed. And the other thing that we need to note is that while we're using this particular index, the physical storage of the data is still the row store, okay, which uses the cluster index on the primary key. So that means that when we perform a concurrent bulk insert, and when the insert happens on the same page, you're bound to have the deadlock issues once more. So we actually went ahead and coalesced the partitions for this particular run in the Databricks notebook. And then we ran the notebook for the ingestion, and then so this is the performance from the database side. Azure Monitor, you notice that I think the database condition is quite healthy. The CPU or IO is not really being throttled, and they are in the comfortable range. But when you look, I beg your pardon. So on this particular chart, what you see is a comparison of how the runs fared against the 3 different approaches. One was using CCI, which is the Azure Synapse Data Warehouse database. And this is with the current run, which is the NCCI, and this is with the pure row store index on the OLTP database. So you observe that with CCI, it just took about 4 minutes, which is about, I think, 250 seconds or something like that. Whereas for the others, it's in the range of it's about 4,200 seconds in the case of NCCI and slightly less than 4,000 for row store index. So the key conclusions that we derive from this are that because CCCI is optimized for this kind of a parallel insert workload, we were able to fully utilize this Spark cluster to concurrently import the data. And the pace at which the insert happens is of magnitude times faster than the row store index. And the other key finding is that With the non-clustered column store index, it does not have much. It does not have this. It does not have the same benefit as CCI. And even though CCI and NCI are based on the same underlying columnar format, NCCI is a secondary index, and the physical storage of data depends upon the cluster row store index on the primary key. So net-net, the performance of bulk import in NCCI is similar to that we experienced for the row store index as well. But the only benefit with the NCCI is that once the data is inserted, we will be able to perform analytics on top of the data. So I think that's the only benefit that we would derive. So let me cover a couple of other points. While I said initially we would cover the scenario only with the Microsoft SQL Spark connector, I thought I'll also give you a flavor of what we came up with in terms of learnings when we compared how it fared against the old Spark connector. So let me not go too much into the details, but probably I'll quickly jump over to the place where we have captured the relative amount of time that the ingestion process took. So you see that you have comparison between the new connector and the old connector for each of the three types of indexes that we use in the databases. So it's pretty evident that the old connector still outperforms uh, the new one. It takes much less time, but we expect that I think the new connector is still in preview, and probably at this time the any bugs or any performance issues might have been tackled. We have not yet run this again with the latest version of the Spark connector, but in case whenever we do that, probably we'll be happy to sort of give an update to the blog post and sort of add those findings as well. So with this, we have done a comparison of the three runs with the three index options. So what remains to discuss further is about the deadlocks that we faced in the runs with the row store and then with the NCCI indexes. And then let's see how actually we can go about mitigating those issues. Next, let us discuss about the deadlocks that we experience when we perform the bulk ingestion into the row store index and then the NCCI index in the SQL hyperscale database. Um, Probably this is best explained by going through the blog itself where we have captured all the necessary details. Um, like we mentioned before, deadlocks happen when two different input processes access the same table and they happen to access the same page. So, which is when deadlock situations can occur. But Databricks is resilient enough, as you've already seen, that it retries and eventually all the jobs succeed. But what can we do to? Why does it happen, and what should we do to mitigate them? So, in order to understand this behavior better, we actually ran this uh, Python code, which actually simulates the situation with which the deadlock situation gets thrown. The data related to stores were actually uploaded, and 11 million records were inserted into the tables because there were six different store IDs. You see that there are six different tasks that are created, one per partition in the ADLS Gen 2 party file. So all of these tasks will execute concurrently on the available workers, and each of them will bulk insert all the data into Azure SQL database. What will happen is that when the bulk insert happens, okay, and then the process tries to obtain a handle or some kind of a lock, an exclusive or an intent exclusive lock on that particular database, it could so happen that two different processes could try to actually acquire a lock on something that the other process has already obtained one. So, which is when it goes into that kind of situation where the deadlock situation happen, and then the Spark job fails, and then it goes into the retry mode, and then eventually it succeeds. And when a particular task on this Spark job fails because of the deadlock issue, then it tries to actually spawn a new job to actually process the whole thing, which is how it retries and then eventually it succeeds. In order to understand and sort of view all these deadlocks as and when they happen, we could actually use this sample script and run this on the master database, and then we should be able to get the details of those logs. And in case you want to run this from the Databricks notebook itself, we could actually embed this query here and then call it from the Databricks notebook. So what you see in the next section is about details about the errors that are written from that particular query, which gives some information about it. And more detailed information is available in the SQL logs directly, okay, where it tells you what is the process ID that actually failed. Okay, and for example, here you see that there was a deadlock that was there's a deadlock that was faced, and there are two different page locks because of which the error happened. And it also tells you which table and sort of it gives you additional information about why that particular issue happened. So how do we avoid this exclusive or the intent exclusive, the Deadlocks arising out of those? So one way to do that is to specify something called a tab lock hint to the database. So with this, the database tries to acquire a table lock. So, but this will only work when the table does not have does not have any secondary indexes. It does not have any index, or when it's a heap table. But in our case, we do have all of those. So which is why actually we get into the situation where and there are two processes which try to get exclusive control, and then they get locked out for that reason. But in the case of the CCGI index, you will realize that actually there are no indexes there. You only have a CCI index. So which is why the same kind of issues did not surface there. And so when there are no such indexes on the table, when you specify the tab lock hint, actually a bulk update lock actually is obtained, which lets you insert data in parallel into the same table without getting into those issues. Okay, so now that we understood how and why the deadlock situation happens, so what could we do to avoid such situation? One would be to actually coalesce all those partitions, which means that it is going to make the insertion a sequential process, which obviously would not be acceptable in most circumstances because it's going to take longer. The other option would be to bulk insert all the data into a SQL Server temp table. Okay, so for every partition, you will end up having a temp table which has all the data for that partition. And then once that all the bulk insert to the temp tables happen, there will be a subsequent or second step which merges all the data from the temp tables into the target destination table. So obviously, it's going to be long term, and this also involves a Spark job to be able to create those temp tables on the fly and be able to perform or trigger those merge operations, which probably might be non-trivial. Okay, while we did not go or we did not try to implement this particular solution, but we pretty much expect that it's going to be it definitely requires a lot of effort. The third option is use the clustered column store index. This is the one that we experienced. This is the one that we use when we worked with Synapse data warehouse database. And then we could see that we could upload all the information within 4 minutes, the 55 million records, and we didn't have a single error out of the deadlocks or any other issues. The other option that is available is to create partition tables. So SQL Server or Azure SQL Database supports the notion of table partitions. So in our case, we already discussed that we have as many partitions in the Parquet as there are store IDs, and we also have those secondary indexes on the tables based on the store ID. So instead of having a single table for sales, we could actually create a partition table where we partition based on the number of values or unique values of these store IDs. So in our case, there are about 1,002 different unique values of the store ID values in the table. So based on that, we could actually go ahead and create 1,003 partitions, and then we could actually then pursue we could actually go ahead and bulk ingest all the data into that. The steps in the subsequent section on this page describe how to sort of create a T-SQL script that will provision those partitions on that particular table, and then how to create the partition scheme themselves. So this is how you create the table which uses those partitions. So last part is actually having created all the tables with the necessary partitions. So how do you import into those? However, by virtue of how we are actually reading data based on different partitions in the party file itself, so that process inherently takes care of making sure that the upload happens, and then it actually each of the data from the partitions will be mapped to the a partition in the SQL Server database as well. So after having done this step, we ran all the database notebooks to put all the information, and then we found that we could actually upload all the 55 million records in in a duration of 593 seconds, so which is actually very pretty quick. And when we actually looked at this spark log, we found that there was not a single deadlock error. Okay, so we just performed this one more step to verify that indeed all the data that was pulled up from the data lake store were uploaded into the Azure SQL database, which was the case as verified here. So this completes the section where we spoke of why those deadlock errors happen on certain scenarios that we tried out during the benchmarking process, and how do you actually make sure that we design for those and we are able to sort of circumvent the issues that we face along the way. There's one more aspect which we also found useful when we performed this benchmark is that after the data is uploaded into the SQL database, in case at some point the data needs to be purged or needs to be deleted. So if we do not partition the table, and when we run the delete operation on the entire table, it's going to take an exceedingly long time. And instead of doing that, so now having partitioned the table, so it will be much more easy for us to delete the data based on the partitions themselves. Instead of doing a delete on the table, you can actually do a delete on the partitions, and that way actually we are able to complete the deletion process very quickly. So this concludes the session where I cover the key aspects of the benchmarks that we captured for the bulk ingestion. So let me at this time quickly walk you through the content in the GitHub repo itself. I think we already looked at the SQL folder, which contains all the T-SQL scripts that were used in the during the exercise, and then we also have included the notebooks themselves. So in fact, you see that they are numbered. The first one is the notebook with which we were able to prepare the data in the AWS Gen2 location so that we could run the benchmarking exercise. So this particular notebook is going to query the pre-existing data in a database. It extracts the information and then sort of writes into a Parquet file and partitions them based on this variety. And once that was done, we could actually run all the benchmark exercises. And each of the notebooks here correspond to the blog article pages 1, 2, and 3 here. And in fact, these are derived directly out of the Databricks notebooks and having published as a blog article. Just note that these are actually Database notebooks itself from where we wrote the article and then it was published to the GitHub location. In this slide, I have included references for further reading. So the three links out here refer to the blog posts that I walked you through for certain sections during this presentation. They contain in-depth information about the different aspects. These are authored by Ankit Sinha, a colleague of mine, and myself. And this is where the GitHub repo resides, which contains the code that was used to run the benchmark exercise. And then we came by a couple of useful documentation related to database indices. The difference between CCI and NCI indices are covered well here. And then the different columns for indices, and then what to use when it's also covered pretty well out here. Related to HTAP and NCCI, so I think they are covered in depth in these two articles. It talks of both the in-memory database options in Azure SQL as well as the non-clustered columns for index to pave the way for HTAP-based capabilities in the database engine. And lastly, most important is related with deadlocks. So this particular article pertains to a previous version of SQL Server, but I think most of the findings and guidance from that are relevant even at this point in time. It talks of the tab blocking that we discussed during the benchmarking exercise, and what is the implication of that, depending on whether the table has a clustered index or whether it has a non-clustered index, and when it has no indexes at all. It also covers this particular section is important, where it covers the ingestion in parallel across multiple on a single table in the database. So how do you actually deal with the various locking behaviors? Here you see that it refers to the fact that when the table has no index, then the tab lock hint provides a special internal lock called the BU lock. This ensures that inserts can happen in parallel. So which is why with the SQL hyperscale, with the Synapse data warehouse upload option, we didn't have any of those deadlock issues. Yeah, so actually it delves into more details around that. I think with that, pretty much I've covered all that I wanted to share with you folks. I hope it was useful, and then I'll be glad to hear from you in case you have any the follow-up question. Thank you so much.